It is a pleasure to introduce Professor Frank Sotil, and he's virtually coming from Texas A&M here to Miami. And it's a great pleasure to introduce Frank. I remember we go way back to my days in Wisconsin. I remember his inspiring talks back then in tropical geometry. I guess he's the person where I first heard the term from. And so it's a great pleasure to introduce Frank with his talk on the irrational toric varieties and the secondary polytope. Frank, well, thank you so much for.
Yeah, well, thanks for inviting me here and having me speak. I've been working in a parallel universe to this for some time, to the topics that all of you are working in. But I've been aware of some of the threads of this, much more so after I completed the work I'm going to talk about. And one of my goals is to sketch how the objects of this meeting, namely toric varieties associated to irrational objects, that they arise naturally from questions from applications. In fact, actually, the toric varieties, in a sense, first arose in statistics in the 1920s, which we called discrete exponential models. And the analog of the moment map also arose in algebraic statistics in 1963. I won't actually talk about that, but what I will talk about, let me try to share my screen.
We're really going backwards in time as the conference progresses.
Yeah. Well, now I'm going a little forward. So you can see on here, there's a picture here you see on the screen. It's a Bezier surface. Now you've looked at Bezier surfaces a lot. I mean, you've looked at, like, say, an airplane wing or the exterior of a car. Those are all designed using using something called well, the area is called geometric modeling, where you represent curves and surfaces on a computer using small data in ways that are easy to manipulate. This is an example of what's called a 3x3 patch, which is actually industry standard. And what you see is a surface that's sort of bluish green, and above it is some cage-like structure. And what I'm going to talk about arose from originally addressing a question that I thought of myself, but Carl de Boer had been asking for some time about what's the meaning of these cage-like structures that the computer scientists drew. And when I first learned about this and the relationship to toric geometry, I understood that they're related to something called toric degenerations. And let me give you a picture of one. So actually, let me go back for a second. So what happens is each of these points you see, these correspond to some integer point in a polytope, actually 3x3 square. And there's a function associated called a Berenstein basis function. And what the patch you see is the function, which is this patch is a graph of, or actually is just the function, is given by a convex combination of these points together, of the actual points you see, multiplied by certain functions with certain weights. And if you vary the weights, you get something that looks like this. Here I'm varying the weights in a particular way. What you saw, the weights were all 1 before, and now they're very large, or some of them are large, and now they're all very small. And what you see is when the weights become large, it's pulled towards the cage. And I wanted to understand this object from geometric modeling. Okay, and I may go back to this picture later on, but let me unshare my screen and do some math. So the story from geometric modeling that I became interested in, it starts around 2000. A Lithuanian mathematician, Krasauskas, he made an observation that the patches that people use in geometric modeling, Bezier curves and surfaces in more general, that they actually come from toric varieties, from the real parts of toric varieties, classical toric varieties. And so I'm going to introduce some notation which will set up where I'm going. So I'm going to let A be a finite subset of the integer lattice. I'm not going to worry about just dimension 1 or 2, but any dimension. And I want this to be finite. And then given this set, there's a map. I like to use the set as an index set, and it takes an n-tuple of positive real numbers to, well, for me, I'm going to take it to the real projective space. And the projective space, it's it's the projective space whose coordinates are indexed by elements of the set A. And now, in fact, because these are non-negative, and you'll see the map, this map actually takes me to what's considered the non-negative part of projective space, which is also what we know as, I'll write this as the standard simplex, one we learned in topology. The map is a monomial map. So I take here an n tuple of positive real numbers, and I'm going to map it to, well, for every coordinate here, I'm going to map it to just the corresponding monomial in that coordinate. So this is, okay, so these are indexed by elements of A. So this is a standard multi-index. So this is x1 to the A1, x to the A2, multiplying all those together. This is just the standard monomial map. It's if you're from toric geometry. And now I want to consider this as a point in projective space, or equivalent to the standard simplex. So one way to do this is really a point in some affine, in some positive orthant of dimension A. I can consider the line, the one-dimensional space that spans, and intersect that with the standard simplex. And I'm always going to be wanting to think of this. Well, sometimes I'll go to ordinary projective space. I want to think of this as a point in the simplex. And it's a little hard to understand how this works, but the non-zero, well, okay, okay. So I'm going to mention there's an action of a group on the simplex, which is more easier to see on the standard, on the positive orthant. Okay. Anyways, the closure of this, of the image, I'm going to just call this YA. This is a real toric variety. I'll call it, it's actually a positive toric variety, because these are positive numbers. I should mention, I made a claim that this has to do with statistics. So the standard simplex is also known as the probability simplex. And this is a parameterization of a subset of the probability simplex given by a bunch of integer vectors. And the subset is called a discrete exponential model in statistics. And people have studied these, in fact, more generally, where these are real numbers for quite some time, over a century. Okay, so but when these are integers, this is really just part of a usual complex toric variety. Although this is not the usual way toric. This is very concretely embedded in projective space. So now, if I take a vector of non-zero real numbers, so this vector is indexed by these elements of A, and so naturally it's you think of this as acting on projective space by scaling the coordinates. And so I'm going to write down the action without saying what it is. You know, there simply is an action here on the positive orthant or real projective space that simply takes a point in here, which to the corresponding the diagonal action. And again, if this is actually in the simplex, so the sum of the values is 1, this will be outside the simplex, but then you normalize it so it lies in the simplex or project it down to the simplex. I'm not gonna worry about what that looks like, because the ideas are more important than the formulas. All right. So the last ingredient. So these are ingredients that come into play in a patch, in the toric patch that Chrysauskas talked about. The last ingredient is just some set of points. So this part is the least important for us, but it's important to understand the previous picture. So you take a collection of points in RD, like say 2 or 3 dimensional space, and then there's a natural map. In fact, it's a parameterization map. It takes the standard simplex to actually to the convex hull of these points B contained in RD. This is the parameterization of the convex hull. Every point in the a point in the simplex is a collection of real numbers, positive real numbers whose negative real numbers whose sum is 1, and you simply take the corresponding convex combination. And what Chrysauskas understood is that Bezier patches they're they're equal to the images of this. So one has this YA that I wrote down, which is standard. You multiply it by some collection of weights, and then you apply this to it. And so the object you get, which is a linear projection of a translation of a toric variety, is a Bezier patch. And the classical cases are when you have when your collection of integer vectors is 0, 1, 2 up to some d, and you're looking at just a rational curve of degree d, or when they're all the integer points in a standard triangle, or maybe some rectangle. Those are classical patches, but Krasauskas realized you could generalize this. Okay, and that's and in fact this picture that we saw. So I'll go briefly to that picture again and see if I can do this quickly. This is an example of such a construction where, again, this is a 3x3 rectangle, 3x3 square, and there are and these blue points are the points B, and there's some weights W I didn't write down, and this is the image of the positive part of a toric variety, and you'll notice that it actually is homeomorphic to a square, because that was the shape I started out with. And so, as I said, Remas realized that you could think about Bezier patches as in terms of toric geometry, and that means you can think about questions about patches using things we know from combinatorics and toric geometry. So Carl de Boer, he's really a giant in geometric modeling and actually a very famous computer scientist who was at Wisconsin, although not when I was there. What he'd asked a question is what is the meaning of this cage? You saw that I drew a cage-like structure over the toric variety. And computer scientists would draw pictures like that, and they call it the control polytope. And what makes this interesting for them is by manipulating the vertices of the control polytope, and maybe these weights that you don't see in there, you can control the shape of a patch in an intuitive way. But it's also a very small data structure, which enables people to store these on a computer. I mean, for instance, an airplane wing may be composed of several million such patches. And that's a lot less data than the actual wing. And an answer to this, so I'm not going to describe this to you, but an answer, or way to begin to see an answer is consider what happens to the patch as these weights vary, as you change these weights. You know, it's known that these weights that I described, they pull the patch towards various vertices, and one way to understand the meaning of the cage is ask what happens as the weights vary. And in fact, what I was interested in, and I sort of understood this at the time, that I thought that this cage should have something to do with the extreme what are the possible extreme positions of the patch, or what happens in the limit as you let the weights vary. Just as a brief aside, I started out all of this with for this description with classical patches. I started out with integer vectors, and it was known from the beginning in statistics that you don't really need to have your exponents to be integer. They can be real numbers, because I'm taking the images of non-negative real numbers, and you can raise a non-negative real number to any real exponent you want. And so I want to talk about, eventually get to what I would call irrational parameterizations, where you have possibly irrational exponents. And what was described before makes perfect sense in that setting, except for the fact that they're no longer algebraic. There's no natural way, although in fact there are ways, as we see from the work people have done this meeting to extend, given an irrational x mode, there are ways to extend this to the complexes, or at least to get some complex information about it. Okay. Now, so that's a goal, but in the case where I have integer exponents, and so I have a classical. In the case of a classical toric variety, so these are a classical toric variety. You may consider the same map, but you apply it to non-zero complex numbers, and you map yourself into complex projective space. But with the same map that I wrote down before, it's a monomial map. There are also, you can also choose weights that are non-zero complex weights, and these guys act on projective space simply by diagonal matrices. So this is a classic case. We're looking at complex toric varieties translated by non-negative numbers. And this question about what happens when the weights vary was studied in the early 1990s in this setting. This was by, let's see, it was Kapranoff, Sturmfels, and Zelevinsky. And what they did is they studied limits of translations of toric varieties as these weights varied. So they looked at algebraic families. In fact, you can see that this complex torus acts on acts on the toric variety, the closure of the image of this, and in fact, it gives you a torus orbit in a Hilbert scheme, and you can ask what's the closure of that torus orbit. I'm sorry, I keep looking at my computer. You can ask what the closure of the torus orbit is, and it's a not necessarily normal toric variety, but you can look at the normalization of that. And they had a little issue about the normalization, but they described essentially what is that locus. So again, you have this torus acts on a particular toric variety, which is the closure of this image in projective space, and that's a locus in the Hilbert scheme of objects of the correct dimension and degree, and you look at its closure, and this torus acts on that closure, and so if you normalize it, you get a normal toric variety, and these were classified, and they addressed what that normal toric variety was mostly. So let me describe it. So their result says is that the space of torus translates of, I'll just say this, sorry, of this closure. So this is a toric variety, is, let's see, is identified with, well, it is a toric variety, but they identify the toric variety. And this toric variety, it's a toric variety of what's called the secondary fan of this point configuration A. So this is a particular fan. It's not full dimensional. Inside of this fan lives inside of the set of all functions from A to R. So there's a particular fan in there. It's not full dimensional. Well, maybe it is full dimensional. It has a lineality space, so the action is not faithful. And another point is the limiting points. So these are originally, I think of these are points on the Hilbert scheme, and so I'm going to think of them as points on the Hilbert scheme. These are what are called toric degenerations. And a toric degeneration, it's a scheme theoretic limit of a torus. So let me just explain. If I take a function from my indexing set A to the integers, I can consider T of A And this is t to the a1. Let's see. How do I think of this? No, I'm sorry. It's t to the lambda a such an a. Sorry, I wrote this on. Okay, so this is an a tuple, and this is an element of the this torus that's acting on projective space. So it acts on the 8th coordinate by this value by lambda of a, and lambda is just some. Okay, and t is a non-zero complex number. So they've identified the toric variety, and the limiting points, the points that are not strict translations of the toric variety, are limits of that toric variety under this one parameter subgroup. So you take what you have the scheme theoretic limit. So you take the limit as t goes to 0. I think and you have t to the lambda. Well, I'm just going to think of I'm going to write this whole thing as t to the lambda that acts on this toric variety, which I didn't give it a name. And this is called a toric degeneration. So the scheme theoretic limit has it. There's a nice structure of these that I'm not going to explain, but briefly, if you consider the graph of this function over A, it lives in n+1 dimensions, and you take its convex hull, you get a polytope in n+1 dimensions, and you look at the upper part of that polytope. The facets you see on the upper part of the polytope give you a polyhedral subdivision of the convex hull of A, and this itself, this is a union of toric varieties, one for each of those polytopes. And the polytope for the original toric variety was the convex hull of A. I didn't, because these are not normal. There's a little bit of an issue as to associating polytopes with them, but they do have an image under a natural moment map or moment-like map to the convex hull of A. And this is the source of my question of Elisa about further subdivisions than these symplectic cuts of Lerman. So for instance, if you start out with, say, these set of 5 integer vectors, you could consider a lifting function that lifts this to height 1 and leaves the other one at height 0, and then you'll get a picture that looks like this. And the limit will be this singular 2-dimensional toric variety will have a limit to 4 P2s, one for each of these triangles, and if you give this a value 1 and these other ones value 0. Now, so I don't want to say much more about toric degenerations. I'll say briefly what the secondary fan is. So the secondary fan lives inside of this space, and this space can be decomposed into rational because A is integer, a polyhedral fan, where the relatively open parts of the cones are those they correspond to the lifting functions that give you the same subdivision in this way. So there's a notion, given a function, you take its graph, take its convex hull, and look at it from above, and this gives you what's called a regular subdivision of this point set A. And those lifting functions that give you the same regular subdivision, they form the relatively open parts of the cones, and that's the secondary fan. So it has, and these are toric degenerations. So this is a result of Kapranov, Sternfels, and Zelevinsky, which they missed the needing to normalize things, but besides that, they picked this out. Okay. So about a decade ago, with Garcia Puente, who was a student at UNAM, and Zhu, who's a geometric modeler in China, we wrote a paper explaining how the Kapranov, Sternfels, Zelevinsky result, what it tells us about classical toric patches like Bezier patches. So even in the case when you have a standard Bezier patch of say 3x3 patch, you need to have the general toric patches to understand the limits of them. And this is published in the so the geometric model is like this. This was published in the ACM Transactions on Graphics, which is what you might call, it's the analog of the annals for that field. But it was, our result was mainly doing what I think of as arbitrage, bringing some ideas that are well known in one part of mathematics into another. Okay, so this timing's fine. So this was written in the case when A is a subset of integer points, and we were able to use a result of this from algebraic geometry using the Hilbert scheme. Now, it was very natural to ask, what happens if you have not a complex toric variety, or the real part of a complex toric variety, but you have one of these irrational toric varieties where you can only talk about the positive real part. So in other words, the exponents are not necessarily integer; they're a real. In this setting, okay, and then this is what I started out with. I have this toric variety inside of the simplex, like in statistics, and I have weights that are positive real numbers, as in geometric modeling or statistics. And now we wanted to understand, we wanted to come up with a version of this Kapranov-Sternfeld-Zelinsky result in this case, but we did not have algebraic geometry to help us. And so, but one isn't bereft with tools. So this translation of this toric variety inside of the simplex. Well, the standard simplex is a compact space. It's a compact metric space. This is a closed subset of it, and so we know that the set of closed subsets of a compact metric space form a metric space themselves. Actually, they form a compact metric space under what's called the Hausdorff topology. And so what we did is we studied Hausdorff limits. So meaning limits in this notion, Hausdorff limits of translations of this positive real part of this irrational toric variety. Using in fact, it's interesting. We did not need to use the space of Hausdorff. This Hausdorff space was compact. What we're able to show is we started with just a sequence of translates, and was able to show that had a convergent subsequence using, using the mathematics at hand. So we didn't need to evoke that the Hausdorff space was compact. Anyways, this actually took a long time because we had to invent some new tools, or maybe just understand some basic facts. And here's, let's see, okay, so I'll give you the result of this. So this is work with Postingel, who's also Italian, and me. My grandparents were from Sicily, and via Misa, okay, via Mizar, she's from Colombia. So I think everybody except for Jew has some, I would say, comes from the Latin world, if not Latin America, in here so far. And anyways, so what we studied is we identified in a sense this space of limits in this setting, and limits of sequences of torus translates WYA of in all of this inside of this compact inside of the simplex. And so okay, so and we obtained an analog, but not a complete analog of the Kapranov-Schoenfeld-Zelinsky theorem. But let me tell you what we obtained. Well, first of all, they all are real toric degenerations. That means they all have the form that they're the limit in the Hausdorff space of, as t goes to 0, of t to the lambda times some weight times ya. So here, if you consider a accumulation point of the sequence, you'll be able to, by picking that accumulation point, you'll be able to find a lifting function. So lambda is one of these lifting functions. There'll be some new weight. I construct from the sequence of weights. These are different w, and it'll be this limit. And this limit has the same picture and understanding as we had as I described over here. In that what you get, what these limits are. These limits correspond to regular polyhedral subdivisions of this point set A, okay, so really identify these, and again, these data can be determined from just studying the sequence. Given the sequence W, given a sequence WI, I can pick out a subsequence of it for which it converges to an object of this form. And two, it showed, because of the parts involved here, this is not so surprising, it showed how this is controlled by this object called the secondary fan of the point set A. And we actually, we delayed publishing this paper for several years because this was not what we were looking for. That I want to say this work failed to achieve its goal. Its goal was to prove a real version of the Kapranov-Schoenfeld-Zelinsky paper to show that the closure of the set of all toric translates was naturally identified with a real toric variety corresponding to what's called the secondary polytope of A. I should point out that the secondary fan, I described it to you. It's the normal fan of a polytope called the secondary polytope of A. And the secondary polytope of A is constructed from all of the triangulations of the point set A. It's a polytope defined by Gelfand, Kapranov, and Zelinsky, and its normal fan is naturally the secondary fan. And what we wanted to do is we wanted to prove what I think is a beautiful moduli result. You have a toric, some toric object, you have torus translations, and the moduli space of all of these, in some sense, is itself again a toric variety. In this case, because of Birch's theorem or the analog of the moment map, each of these objects is homeomorphic as a manifold with corners to the convex hull of the point set A. And so we have these curvilinear versions of a polytope in this simplex, and we like to identify all possible limits of that with another polytope called the secondary polytope. And we couldn't do that. We came very close. And the problem, so the obstruction was the lack of a construction of a toric variety, maybe certainly rational, from a fan. Now, of course, in this conference, people had a construction of something of some toric variety from a rational fan, but we wanted one which was in this category of just real analytic subspaces. Well, that was solved, and in fact, the solution is quite simple in this case, and this was done with Atta Pierre, who was a graduate student here at Texas A&M. And let me just give you the pieces of it. I don't have to say too much because most of us are familiar with how to construct a toric variety from a fan. Okay, so I'm going to use some notation which people in toric geometry use. N is going to be Rn. This is going to be like my space of co-characters. And then M will be the dual space to N. I think of this as characters. I mean, they're really just vector spaces written additively. And now the construction of a toric variety, you need to associate some space to a cone. And then if you do it right, everything glues together. So that's what the case here is. So I'm going to let sigma contain N be a polyhedral cone. So it's given by intersection of finely many half spaces. They can be irrational, and then it has a dual. Its dual is those elements in the dual space, such that when I pair M with an element of the cone, it's not non-negative for U in the cone sigma. It's the usual dual. And then I'm going to associate a topological space with a natural topology to this cone by looking at the dual cone. And this is, I'll call it Hom C sigma dual into the non-negative reals. And what is this? This is the set of all semigroup homomorphisms. So this is an additive semigroup, meaning you can add any two elements together. It has an absorbing element 0, which has an in it. And this is a semigroup. It's a, well, yeah, no, I'm sorry. This has an identity element, namely 0. This is a semigroup. It has under multiplication as identity element 1. It also has an absorbing element 0. So semigroup homomorphisms from this dual cone to the non-negative reals, which are, okay, so because it's a semigroup, it has to take the identity in this cone to the identity in the non-negative real numbers. And I want phi is continuous on phi inverse of the strictly non-zero real numbers. So it doesn't need to be continuous everywhere. It needs to be continuous where off of the absorbing element. And
sorry, just to make sure I have understood. So you take this is a condition on your homeomorphisms that have they have to be continuous.
Yes.
Okay, thank
you. And this is because I actually don't have. So one thing that's missing here is a quasi-lattice, and if I had a quasi-lattice, I think that this would take care of itself. That's one thing I want to mention that we didn't introduce. We didn't really think about it here. So this is actually quite natural because every cone it has ideals, and the ideals, well, you'll see if you look at phi inverse of this is a face of the cone, and ideals on a cone are complements of faces. So this is fairly natural, and so one of these maps, you pick a face of the cone, it's continuous on that. Okay, so it's the usual continuous map from an additive group to non-negative reals given by exponentials, and off that face it's 0. And also this guy has the weak topology of point. There's a standard weak topology on any space of this given by pointwise evaluation, and it turns out that under this it's not so weak because it's homeomorphic to the original cone N. I mean, you can identify it as in terms of also with the boundary. I won't get into that too much because we did not include functions in this setup. Some aspects of this homeomorphism aren't as sharp as they should be in terms of the corner structure of this. Anyways, so there's this construction, and from it, there's the usual that if I have one cone containing another, that implies that this, because I'm taking essentially double duals, that you have containment of these open sets. And then given a fan sigma, you can construct Y sigma, which is simply the union over all cones in sigma of these together with the natural identification. It's the same construction as you do with a complex toric variety. And I think it's also the same construction as you do when you associate one of these more exotic spaces to an irrational fan. In fact, all that I'm doing here is I'm looking at the real points of that construction. I mean, as I understand it now, I've thrown away information related to quasi-lattices or lattice and just looked at the real points of that construction. And this is what you get. And let's see, I'll just say, okay, so I'm sorry, I don't have examples because I'm doing a board talk. I'm sorry about that. Yeah, should I say what the weak topology is a sequence of functions converges if and only if for every point in sigma hat, sigma dual, the evaluation of the function of those points converge. I mean, so I'll just give an example. So suppose I have sigma is just the positive part of the reals. Then sigma, well, it equals sigma dual, and what does a typical function in this space look like? Well, it has to take 0 to 1, and then it's given by it's actually, you know, because it's a continuous homomorphism, it's given by its value at 1. And so if you pick a value at 1, you discover it's an exponentially decaying function at 1. And if you take, you know, any other value, its graph is going to look like this. But what happens is if you take a sequence of points that converges to 0, this is going to converge to a step function, which is going to be on this face, it's going to take you know, on this face, it's going to take the value 1, and on this face, it's going to take the value 0. So this is what I mean. It's continuous off of, you know, on the place where it doesn't take the value 0. So in this case, there's only a single point, so that's not a very strong condition. But these are what these functions look like. And well, so let me just state some properties of these. So for any fan in N, well, the first thing is if sigma is rational, then this construction is the positive part of the corresponding complex toric variety. Every complex toric variety. So toric varieties, you should think of them as, okay, we think of them as some complex space we associate to a fan, but what it really is, it's a functor from fans to semigroups. And if my semigroup is the complex numbers, I get the complex toric variety. If my semigroup is the real numbers, I get the real toric variety. If the semigroup is the non-negative reals, I get the positive part of it. If the semigroup is, say, the integers, then I'm going to get essentially the integer. I'm going to get this fan intersect with z to the n. So that's okay. So let me talk about some other points. So it's well, it's an equivariant cell complex. And what is it equivariant for? Well, I can think of this group N. Well, okay. So the group N that I started out with, if I write it down multiplicatively, then this acts on this. I'm sorry. So we get Y sigma. So Y sigma, it's an equivariant cell complex, and it has one orbit for each cone. And in fact, the orbit for the cone sigma, what it corresponds to, it's a quotient of n. It's n mod the linear span of that cone. Naturally, under this action. Again, I'm writing this additively, but I think of this action as multiplicative. Each orbit has a distinguished point in the same way that a standard toric variety does. the closures of orbits, these links that we saw earlier, also occur. However, the normal structure is lost in this setting. So the closure of this orbit, it's naturally identified with the toric variety for the fan modulo this. Well, okay, I'm sorry. I should say that this right here, this object, this is the link of the cone. You take a point in the relative interior of the cone, and you just intersect the fan with a small neighborhood at that point, and then quotient out by the cone. Also, this map, this is functorial for maps of fans. We could not show that it's an equivalence of categories because we didn't include functions or quasi-lattices. Other things that this is compact if and only if the fan is complete. That's and the proof of this used the same arguments as Postingel, Villamezar and I used. And if sigma is the normal fan to a polytope, then this equivariant cell complex, it's actually so the polytope, I'll call it P, it's actually homeomorphic to the polytope P. This is non-canonical because you have to choose some points in P whose convex hull is P. And given that choice, there's a map from this object to a corresponding projective space whose image is this toric variety what I called Y sub A before, and that's naturally homeomorphic to P under a version of the moment map due to Birch from 1963. This is this uses what's called Birch's theorem, which was this precursor to what we think of as the moment map. And a consequence of all this, once all of this was proven, then it's possible to show our original goal, which is that the Hausdorff space of torus translates. So it's I consider all torus translates, and I take the closure in this original setting is homeomorphic to, with choices, to the secondary polytope of A. So that probably all went fast at the end because I'm writing on the board, and my handwriting is really pathetic. My students complain about it, but that's what I wanted to say today. The story here is that objects will parameterize toric varieties given by real exponents inside of projective spaces or simplices. If they arose in other parts of applied math, and it's natural to ask some questions which you may look at in ordinary toric geometry, such as the moment map, also known as expectation in statistics, or toric degenerations, or even torus translates arise in these application areas. Maybe they're not of central interest there, particularly the latter question. And in order to address them, we were led to construct a theory of these positive real parts of toric varieties associated to irrational fans. And these are ordinary Hausdorff spaces. And one obtains this moduli result eventually. That's what I wanted to say. I hope, thanks for your attention, and thanks for listening. And that's it.
Thank you so much. Is there any questions from anyone in the audience? Okay, if no one else has a question, let me ask. So presumably, from what you say, in the irrational toric varieties of ELISA, one would presumably have, and also for the quantum toric
exactly
stacks,
they both contain this inside of them.
Yeah. Also the quantum toric stacks contain this thing inside, of course. So this, and then you talk about this functoriality, which for the quantum toric stacks, the morphisms should coincide. Unfortunately, the morphisms of quasi-faults and the morphisms of stacks do not coincide. But my impression is that the morphisms of the quantum toric stacks would coincide to make this functorial.
Yeah. Well, the data you need is, so this is a fan, and for me, I didn't look at any other structure, but you would need to have a I don't know the term you use. I'll use quasi-lattice for which this is a fan in that quasi-lattice or its dual. I mean, because we
call that a quantum fan. Yeah.
Yeah, the quantum. Yeah, you need the quantum fan where you have essentially functions for which you know, when I say functions, I mean literally just points in Rn that the linear. I mean a point in Rn is both a linear function and an exponential function. So I think of it as an exponential function. But you need those for which the fan is makes sense. And once you have that, then you of course have maps of fans, and this object doesn't care about your functions, because it's rather naive, but it gets carried along, and so this object will be inside of your quantum toric stacks, and I think it's also inside of the quasi-folds. I mean it's like an orbit space, because in fact actually this moment map, it's identifying an orbit space, and every orbit should go through one point of this.
That's right.
And also I should say that in this really naive setting of Birch's theorem, so when I talk about the moment map, what they look at is they're looking at positive real points, and they're just looking at this projection where you take the absolute value of the point and you map it to some fixed point, like an expectation, like a probability measure, and the ordinary moment map factors through this linear map. So that's that. Yeah. I mean, when I first, even in the last talk, the objects we saw in the last talk, there's something like there's a positive part associated to them, and this also each their moment map factors through this object.
That's right. Also, just to relate everything to everything else as it should be, there is also this. You just said that there is this functor to semigroups.
Yes. So, yes. So if you have so just fans in a vector space, you might have to enrich them in your setting. But these, there's a functor from fans to semigroups. You have to know. I mean, as I explained, we construct a toric variety by you take a cone, you take its dual, and you take hom of that dual into a semigroup with some conditions. And given that, once you decide what that hom functor is, you then get a functor on fans. And in that sense, a toric variety is I can think of this toric variety as a semigroup valued functor from fans to different semigroups. In the same way that an algebraic variety involves a functor of points. What?
Could we see tropicalization in this fashion?
I think if you tropicalize, you're just going to get the fan back.
That's right. And the other question,
or the polytope.
What if we put some semigroup associated to the quaternions? Then should we get the quaternionic ones?
Don't know.
That's Alberto. That's a question for you.
Sorry. What's the question? Sorry. If you take values in a semigroup special like the quaternions, My answer is I don't know, but it's very, very interesting. I was thinking about it during the talk. Because
yeah. I mean, I didn't. I mean, I sort of knew this in graduate school that toric varieties that you think of them as being the semigroup valued points of a fan, considered as a function from fans. And it depends on the space of fans you deal with. But I really realized that here that it's really quite natural to think of you have some category of fans with maps. You pick your choice, and then you can talk about of course, inside a cone is a fan, and if you understand how to associate a cone to something with a semigroup map, then you get a functor from your fans to that object. So it's a semigroup valued.
Exactly.
Your toric variety is actually the points in when you apply this functor to that semigroup.
Exactly. Let me make a comment. So essentially, we'll map from monomials to some projective space. But in the quaternion settings, if you have a monomial, let's say Q1 to the N1, Q2 to the N2, etc., your options are very, very complicated because they don't commute. So you may have, for instance, x squared times q to the third power, but you could have also q, p, q, q, p, all the extrapolations of the monomials. And so I think the natural setting would be into, you take all possibilities.
Yeah. Well, so this idea of a parametrized map, a monomial map, may be difficult with quaternions because they're non-commutative.
Exactly, but you take them all. Maybe, you know?
Yeah. I think it'd be interesting to think about what you would get, because so one of the things that I find interesting about ordinary complex toric varieties is that you can think of them naively in terms of the closure of an image of a monomial map, and that they arise in applications this way. You can also think of them in a very, I think, sophisticated way, which relates to symplectic geometry. In terms of, well, what you can think of them in terms of fans, or you can think of them in terms of polytopes, which is somehow a mixture of the two. And the polytopes are related to, I think, symplectic geometry. And this fan is very much an algebraic geometry construction. That's why you have your quantum fans. And for some things, you need to consider all three versions of toric varieties together, because they're all slightly different.
That's right.
A very interesting question. I think about it.
Okay. And when we can travel again, I'll visit you and we can talk about it.
Very good.
Fantastic.
But we have to wait a little bit, I think.
Yeah, I'm afraid it'll be a while.
Exactly.
I mean, my university. Ask a question?
Go ahead, sure.
No, sorry, I didn't want to interrupt
please,
Alberto.
No.
Okay, so just to, I don't know if I have well understood, but you said that Y sigma is homeomorphic to the moment polytope, and it can somehow be seen inside the toric quasifold. So can it be that it is actually the quotient of the toric quasifold by the quasi-lattice that actually gives an object that is homeomorphic to the polytope, to the moment polytope?
What I suspect it is so inside of your toric quasifold, you have somehow there's like a small thin real part of it, and which is transverse to these orbits
yes.
and that this actually can be, well, when this is a polytope, this actually can be just slipped in. This can actually be identified as being right in there, actually, as those points.
Yeah, I mean, I agree. So transverse to the orbits means that the quotient is, okay.
Yeah, but I think actually, I mean, we have this in ordinary toric varieties. The positive real part of the toric variety, it meets every orbit of the compact group.
Yes. Okay.
So by only looking at generalizing the positive real part, I didn't have to think about what the unusual topology you get.
Yes.
What happens with the complex points.
Yes.
But you also miss the functions, and because of the functions, you can't show that there's an equivalence of categories, which is a weak point of this theory.
Yeah. Thank you.
Yeah. Which you do get with the quantum toric varieties, this equivalence of categories, of course.
Yes.
Yeah.
because you're starting from a fan construction and really enriching, constructing things. You keep all the data. I was impressed when I looked at your paper and saw you speak that that I'd realized we were ignoring the functions and didn't know how to put them in here in a way which fit well. And when I saw this aspect in your paper and your talk, although I didn't understand all of it, I realized that was actually the missing piece, and that's one reason why you're able to get this. But of course, you also get a very, very rich structure outside of it.
That's right. That's right. And a question that we should explore is the relation between this your theorem with the secondary polytope and the modular space of quantum toric varieties that arises from just all the deformations at the same time.
Yes. There should be a relation. Now, I mean, one thing that I like about these objects here is you can deform the fan or the polytope, and that's a little bit harder if you have the equivalent of a quasi-lattice, because that's somewhat of a rigid structure. But perhaps there's a way to understand this as you deform those objects as well with the fan.
That's right. Exactly. Yeah, you can also deform the quantum lattice. Yeah.
Yes. Yeah. You have to deform the quantum lattice. But I think early in my career, after I'd learned a little bit about toric varieties, I was really struck by this moduli space result. That geometry. One of the things that's wonderful about geometry is we have geometric objects, and we consider families of them, and these families are naturally also geometric objects. And in the best possible case, like this, they're the same type of objects as we started out with. I mean, it just doesn't get better than that. This is one thing I think is really interesting.
Beautiful theorem, yeah. You got a beautiful theorem.